everyone. Again, what we're going to talk about today is how you solve a spectroscopic unknown. Sometimes you're given an unknown and you have to figure out what it is, right? And so how do you do that? So the very first thing that we're going to do, which is not really related to spec unknowns, but is something that we do consider and something you can use really anywhere in class, and that is figuring out how many degrees of unsaturation are in your molecule. And so again, it tells you a little bit something about structure, and it can be helpful in solving all kinds of problems, especially word problems, ABCD problems. It's not very hard to do, so we're going to go ahead and talk about it now, and then we'll move into solving spec unknowns. So, calculating degrees of unsaturation, oftentimes we just shortcut that and say DUS. And so what you need to remember is that each double bond is 1 degree. Each ring is 1 degree. Each triple bond is 2 degrees of unsaturation. And it doesn't matter, but I mean, you can figure this out. Each aromatic ring, right, because the aromatic ring is first of all a ring, so that's 1 degree. And then it has 3 double bonds in it, so that's 3 more degrees. So each aromatic ring itself would be 4 degrees. Okay? So that's how these things are counted. So, right, how does that help? You got to see what part of the board you can see. Okay, so if you have, let me put you over here for a minute. If you have a simple hydrocarbon, and we're going to use, for example, C15H28. So if I have a molecule C15H28, and I want to know a little bit about it as I'm trying to figure out what the structure is, first thing I can do is figure out how many degrees of unsaturation, right? That will help me understand if there's any, and you know what that might be. And so the way you do it is the very first thing you do is you compare to the saturated case, right? And so remember that the general formula for figuring out if something is an alkane is C to the N, H to the 2N plus 2. So when we say compared to the saturated case, that means if I have a molecule that has 15 carbons, then the saturated molecule would have, and again, if N is 15, H would then be 2N plus 2, would be 32. So, now I've calculated that. The next step, essentially, is to take the number of hydrogens in the saturated case, which is 32 in this case, and subtract the number of hydrogen in your actual molecule, right? And you have 28. And so when you do that math, you get 4. And then the third step is to simply take this number and divide by 2. And in this case, it gives me 2. And so that tells me that this molecule has 2 degrees of unsaturation. It doesn't tell me what they are. Right? It could be 2 double bonds, it could be 2 rings, it could be 1 triple bond, it could be 1 ring and 1 double bond, right? You don't know that, but you know that that's all that is present in this molecule, right? Which isn't a lot, when you have 15 carbons in your molecule. So that's how you calculate the DUS when you have a simple hydrocarbon, meaning just carbons and hydrogens. Right? The process is always going to be the same, so just remember this process. But let's look at, right, because many organic molecules have atoms besides just carbon and hydrogen. Let's look at what happens if you have other types of atoms. So what if you have halogens, right? Halogens count as, and I'll put count in quotations here, halogens count as hydrogens. So, try to look for my example. If you have C4H6Br2, then, right, I'm trying to get this in this form. And so my halogens count as hydrogens, which means that this really looks like C4H6 plus 2 would be 8. Right, so it really looks like I'm working with C4H8. So then step 2 would be to compare it to the saturated. C4H10 is the completely saturated case. 10 minus 8 gives me 2. 2 divided by 2 gives me 1. So I know in this molecule, I have 1 degree of unsaturation. So that's how it works if you have a halogen as part of your molecular formula. What if you have oxygen? That's a pretty common, right? That's a pretty common atom in organic molecules. So the beauty of oxygen is it can be ignored. And so you don't have to worry about oxygen. So if you have C20H34O2, that looks like C20H34, because I can just ignore any oxygen that I have. The saturated case, C20 would be H42, right, because that's 2N plus 2. It's my saturated case. Then I take 42, and I subtract from it 34, and in this case I get 8. And 8 divided by 2 gives me 4. So I know I have 4 degrees of unsaturation in that molecule. And then the last very common element is nitrogen. And for each nitrogen, right, you subtract a hydrogen. So if you have 4 nitrogens, then you would subtract 4 hydrogens from your molecular formula. As an example, C8, H13N becomes C8H12. Now compare to C8H18 would be the saturated case. 18 minus 12 gives me 6. 6 divided by 2 gives me 3. So now I know that there are 3 degrees of unsaturation in that molecule. Okay. So it's not hard to do. If you have a molecular formula, it doesn't take very much time. but it does give you a little bit of information. So, before we move on, let's go ahead and have you practice a few of these. So I would like you to calculate the degrees of unsaturation in the following 4 examples. C40, H56, C9, H16, BR2, C6, H5, NO2, and C20, H43, Cl2, and 3O4. All right, go ahead and write those down and then pause the video and figure out the degrees of unsaturation. And so you've now come back, and ideally you got the following answers. This should have 13 degrees of unsaturation. This should have 1 degree of unsaturation. This should have had 5 degrees of unsaturation. And this one actually has 0 degrees of unsaturation. So if you have any questions, hopefully you can see that. Right. If you have any questions about how I calculated any of these values, be sure to let me know. And remember, you should never, ever, ever come up with a half, right? They all need to be integers, right? Because you can't have a half a degree of unsaturation. All right, so that is just calculating degrees of unsaturation. That is in your book. And is helpful in many, many kinds of problems. All right, so now let's talk about solving spectroscopic unknowns, or we shortcut this by saying solving spec unknowns. This is actually what you're going to be doing in lab next week. So we're going to do a little practice now. And so, you know, is there a set algorithm that you should follow to do this? No, it's really sort of taking all of the analytical data that you collect and making sense of it so that you end up with one molecule. The beauty of this is that when every single piece of data fits your molecule, then you know you have the right answer. And if there's some piece of analytical data that doesn't match your molecule, then that should be an indication to you that you don't have the right molecule. You should go back and look at things. And so I'm going to put up sort of a little plan that you can follow to sort of help you think your way through these. It's not that you have to do this, but these are sort of the way I approach these problems. So the very first thing I do is calculate the degrees of unsaturation, right? That gives me a little bit of sense of what my structure might actually look like, right? Just in a saturated, unsaturated sense. The next thing I do is I analyze the IR, and what the IR will tell me, what we look at IR for, are our functional groups. So again, I know from the molecular formula if I have any heteroatoms in there, and so that starts to get me to think about functional groups too. The next thing I do is analyze the C13 NMR spectrum. And that's going to tell me 2 things. It's going to give me a little information about symmetry and I'll call it chemical shift. Right, so if I use my molecular formula and I know there's a certain number of carbons, then I look at how many I see, and that tells me whether I have complete symmetry or partial symmetry. I also look at my chemical shifts. That helps me figure out also functional groups based on where different carbons absorb. The next thing I do is, of course, analyze the proton NMR spectrum. And really what I'm looking for here, I mean, you know, finish this, splitting patterns. You know that when we look at proton NMRs, we pay attention to chemical shift, we pay attention to integration, but really we pay attention to splitting patterns. So I am paying attention to all of those things, but it's probably the splitting patterns that are going to help me really build this molecule. And then the last step is actually probably the most important, and that is to recheck. It says recheck. Recheck all data. Right? Sometimes when you move between these pieces of data, you sort of forget something, or you add in a carbon, or you don't have enough hydrogens, or all kinds of things, right? So after I do this, and I'm pretty happy with the structure I have, I make sure I go back and recheck all the data. And that really means looking at my degrees of unsaturation, looking at my molecular formula, right? Because that'll tell you whether you added or subtracted any atoms, and then making sure that everything I thought to be true in these types of analytical, in these spectra, actually are true in my product. So let's go ahead and use this method to look at a few problems. Okay, so you have this handout. It's called example 1. You can see up here the molecular formula. Let's see if I do this. Can you see it on your screen? Move it down a little bit for you. Oh, but you don't need to see it on the screen because you have the piece of paper. Right, so the molecular formula is right here, C8H14, right? So it's a hydrocarbon. I have nothing but carbon and hydrogen, so I don't have to worry about any of the oxidative functional groups. If I calculate the degrees of unsaturation, I get 2, right? So I have 2 degrees of unsaturation, right? Because this would be C8H18. 18 minus 14 is 4. 4 divided by 2 is 2, so I have 2 degrees of unsaturation. Now I'm going to look at my IR. And if I look at this IR, I really don't see a whole lot, right? I see carbon-hydrogen saturated here. I don't really see anything, and then I see fingerprint. So the IR in this case is really not terribly helpful. But that doesn't surprise me because it is only carbon and hydrogen. And so now I'm going to look at the C13, which is on the bottom of the sheet. And if I look at the C13, I see 1, 2, 3, 4 peaks. I see 4 peaks, but I know that I have 8 in my molecule. And so if there are 8 carbons in my molecule and I see 4, now I know I'm dealing with a completely symmetrical molecule. These are alkane-like carbons, and this carbon down here is telltale, but it's also very interesting, right? That's really going to help you solve this particular problem. And so let's go to now the proton NMR, which you can see. So for the proton NMR, first of all, if I see my integrations, I see 3, 4, 5, 6, 7. So I see 7 hydrogens. But I know I have 14 in my molecule, so really all of these are double. But that's because I have a completely a completely symmetrical molecule. I see the pattern of 2 hydrogens, so a CH2, a CH2, and a CH3, right? Those are the groupings that I have. I see a triplet, a multiplet, and a triplet. So you'll start to get used to seeing this pattern. And so if I build this molecule, I'm going to say, you know, I have this triplet here, which is a CH3 group at, you know, about 1. And it's split into a triplet. So it integrates to 3, but it's split into a triplet, which means that how many neighbors does it have? Right, so it has to have 2 neighbors because 2 plus 1 would be 3. It would show up there. Right, so I've done this. And if I want to look at this triplet, right, so now I'm looking, and this is a CH2 because it's 2 hydrogens. It's also split into a triplet, so it also must have a CH2 next to it. So this is my first triplet. This was my triplet here. And that leaves me with the CH2 in between. And as you can probably piece this together, the CH2 here and the CH2 here are the same CH2. So I have a C, CH, 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 CH. Right, so CH2, CH3, and then my center, which would in fact be a multiplet, right? Because these hydrogens are split by that and by that. Okay, so now I have this piece, and I know I have 2 of them because I have a completely symmetrical molecule. And so the question is, how are these 2 pieces connected? Right? How do I take these 2 pieces and connect them? Well, so far I've used 1, 2, 3, 4, 5, 6 carbons, and so I have 2 carbons left. And I've used 14 hydrogens, so I don't have any more hydrogens. So what could be here and here with no hydrogens on those carbons? That would have to be those 2 carbons connected by a triple bond. And this is, in fact, your molecule. And this triple bond, right, explains the carbon around 80, and also explains the 2 degrees of unsaturation, because a triple bond is 2 degrees of unsaturation. The only question you might ask is, why don't I see the triple bond in the IR spectrum? And the reason you don't see the triple bond in the IR spectrum is because when triple bonds are symmetrical, they don't actually show their peak. Right? So that stretch, the carbon-carbon triple bond stretch, is generally a weak stretch. Get rid of this. Right, it's generally a weak stretch, and it's generally in this area of the spectrum, right, around 2100 to 2300. But if you have a symmetrical triple bond, then you actually don't see that stretch. So that's why you don't see it here. And that's why you have to use all of these different pieces to try to figure out what your molecule is. But you just solve that molecule. It is 4-octine. So let's have a look at the next example. Example number 2 on your sheet. This time I have a molecular formula, C7H14O2. Go ahead and calculate the degrees of unsaturation there. Remember, oxygen can be ignored. So you come up with 1 degree of unsaturation. Now I'm going to look at the IR. And this time, this time I see something really distinctive in the IR. Get rid of this background stuff. Right, and what I see in the IR is carbon-hydrogen stretches, but bam, 1734, I think that says. Right, so here I have a really nice carbonyl. And so now I know I have a carbonyl in my molecule. And since a carbonyl is a double bond, that double bond takes care of my 1 degree of unsaturation. Right? It doesn't have to be a carbon-carbon double bond. In this case, it's a carbon-oxygen double bond. That's my 1 degree of unsaturation, so I can't have any other type of unsaturation in my molecule. And then I just see fingerprint, so that's the IR. Let's go to the bottom. Right, if I look at my carbon, I see 1, 2, 3, 4, 5, 6 peaks. Right, this triplet, those 3 peaks, just ignore that little thing. That's actually CdCl3, which is the solvent we use to collect these spectra. So 1, 2, 3, 4, 5, 6 carbon peaks I see. My molecular formula has 7 carbons. So now I know that I have 1 carbon that is repeating itself, right? So a little bit of symmetry. My guess is just going to be this one because it's so much taller than any of the other ones. So I'd probably think, okay, you know, that's where my 7th carbon is. What else do we want to talk about? When I look at this, these are alkane-like carbons to me. When I see this peak around 68 or so, that says to me, oh, that might be a carbon singly bound to an oxygen. And then when I look down here, right, that's clearly a carbonyl carbon, not an aldehyde or a ketone, but any of the others. And so I'm going to go back to my molecular formula where I recognize that there are 2 oxygens. I know one of those oxygens is making up a carbonyl. And so I'm going to guess at this point that perhaps what I have is an ester. Because if I have an ester, then I have a carbonyl, and I have I've used my 2nd oxygen, and I would have something bound to that carbon, which would probably show up here. So I'm starting to think that I have an ester. So now let's look at the proton spectrum. So when I look at this proton spectrum, I see 1 hydrogen here, CH. I see it very far downfield, right? It's about 5. Whenever you see a gap like this, it's just that since there's such a gap between 2.5 and 4.5, and there's nothing in there, they just cut it out and condense it onto one piece of paper for you. This is just simply a blow up of that. But you know, I see this and I'm like, ooh, that's pretty far downfield for 1 hydrogen, right? Then I look here and I see a 2 CH2 triplet, a CH2 multiplet, a CH2 triplet. Perhaps you've seen that pattern before. And then here I have a 6 hydrogen doublet. Right, so as soon as I see 6 hydrogens, I think, that's 2 methyl groups. And if I have 2 methyl groups and they're split by 1 hydrogen, because it is a doublet, they're going to be split by 1 hydrogen. Right, I start thinking this 1 hydrogen and these 2 methyl groups are coupled to each other. They split each other. Right, and that starts to explain why there's so many peaks out here. You will also recognize, not only you recognize this as a common pattern, you will start to recognize 1 hydrogen multiplet, 6 hydrogen doublet as a classic isopropyl type splitting. So let's start putting this molecule together. I'm going to start with my ester. And I'm not going to worry about this side right now. But I know from this peak here, pulled down to 5, that's probably the carbon that is bound directly to that oxygen, because there's nothing else that really would be pulled that far downfield. And this is one hydrogen. So I know that I have one hydrogen there. And I know that whatever is here and here cannot be hydrogens. And since they can't be hydrogens, right, they have to be carbons. And again, we already talked about how this one hydrogen and these two methyl groups are related to each other, right? The one hydrogen splits these into a doublet. So these are actually CH3, CH3. This is my isopropyl group. And I know that it's bound to the oxygen because this is the hydrogen that gets pulled furthest downfield. And so now what I'm left with is CH2, CH2, CH3. If you remember that pattern from the previous problem, you'll remember that it's CH2, CH2, CH3, right? So this CH2 is here. This CH2 is my multiplet. This CH3 is my triplet. And so my molecule, I'll draw it better for you. Will look like that. That's on your screen. There it is. Now it's on your screen. Okay. So we would call that isopropyl butanoate, but you will learn to name that pretty soon. Just some points for you to remember, right? The isopropyl, classic isopropyl pattern is a 1 hydrogen, 6 hydrogen, 1 hydrogen multiplet, 6 hydrogen doublet, and then this CH2, CH2, CH3, triplet, multiplet, triplet. That is a classic propyl pattern, right? Propyl and isopropyl. All right, and then again, if I go back and check everything, my 1 degree of unsaturation is here. These two carbons show up the same, so I would expect to see 1, 2, 3, 4, 5, 6 carbons in my spectrum. This one would be furthest downfield. This one would be between 60 and 80, and the rest are sort of alkene-like hydrogens. I have the right molecular formula, so I'm good. I'm confident that is my solution to problem number 2. And so the last problem I have for you, example 3. Get rid of this. Okay, so problem 3 has a molecular formula C16H22O4. Go ahead and calculate your degrees of unsaturation for that. And ideally you came up with 6 degrees of unsaturation. Now we'll look at our IR. Our IR shows us not really anything, some CH saturated, nothing, and bam, another carbonyl, and then fingerprint. So again, I have a carbonyl. I look at my 4 oxygens, and I think, oh, okay, what am I going to do with that? But that, we'll talk about that soon. Now I'm going to look at my carbon. I have 1, 2, 3, 4, 5, 6, 7, 8 peaks in my carbon spectrum. 8 peaks in my carbon spectrum, 16 peaks in my molecule, complete saturation. I'm sorry, complete symmetry. Symmetry. Right? So if I have 8 here and 16 in the molecule, then I have a completely symmetrical molecule. Right? That's really helpful. When I look at this spectrum, I see this as my carbonyl. This to me looks like it's in the aromatic region. This looks like it's a carbon bound to an oxygen. And these look like they are aliphatic carbons, or alkene-like carbons. I know I have, it's completely symmetrical. I know I have a carbonyl. I only see one peak here in the carbonyl. I see an aromatic ring. So I'm going to think that I have an aromatic ring in there, which is 4 degrees of unsaturation. If I have a completely symmetrical molecule, not only do I have one carbonyl, but I have 2. So that takes up my 6 degrees of unsaturation. And I start thinking about this peak here, again, a carbon bound to an oxygen. That makes me think I have an ester. So I can use my carbonyl and my oxygen to be an ester. And again, remember, I have 2 of them. So those are some big pieces that I've already solved. And now I'm going to look at my hydrogen spectrum. Again, I have a gap in here, but you can look at this molecular formula, or I'm sorry, you can look at this chemical shift, and that really just confirms that these are in fact my aromatic hydrogens, right? That I do have an aromatic ring. Again, I see the integration of 2. If I say 1, 2, 4, 6, 8, 9, 10, 11, I have 22 in the molecule, so again, complete symmetry. This is going to tell me I have truly 4 aromatic hydrogens. And I have a CH2 triplet, CH2 multiplet, CH2 multiplet, CH3 methyl group triplet. So I'm not going to put this all together for you. I'm going to go ahead and leave this video here and let you figure out what the actual structure of this molecule is. And then you're going to go ahead and just give me that in class. So I hope this helps you sort of figure out how to think about unknown molecules when you've collected lots of data for them, and start to have to think about how am I going to put this molecule together, right? Just do it bit by bit, and then you will actually get to the correct answer. So again, as always, if you have any questions, please let me know. Otherwise, I am sure you are going to be fantastic spec unknown solvers.